Chapter 11, Section 1 is about inverse variation, and we're going to talk about the different ways that things can be related to each other when we're talking about graphs, and we're going to spend more time talking about the inverse variation in this section because we're going to get into what the graphs of the inverse variation look like, because a lot of what this chapter is going to cover is going to be dealing with these rational functions, where you have fractions, and within the fractions you have expressions that involve like an x squared, an x, and a number. So we're going to talk about inverse variations today to kind of get us started with understanding what these graphs that we're going to see this chapter look like. So the first type of variation I want to go over with you guys, which we've talked a little bit about this in the past, is called a direct variation. So what a direct variation means is that your variables like x and y are going to be acting the same. So for example, if x gets bigger, y also gets bigger. If x were to be getting smaller, y would also be getting smaller. The equation that we see with direct variation looks like this. Y equals kx, where k is going to be your constant of variation or the slope. So back in chapter 4 when we talked about slope for the first time, we saw a direct variation when we were graphing things that said like y equaled 2x or y equaled negative 4x. So it's very similar to the form y equals mx plus b, where we have a y-intercept of being 0. So these graphs like go through the origin, they go through 0, 0. And your slope, m, is being taken place of that k for right now when we're talking about these constants. So k is the same idea as what slope is. So let's take a look at an example. Now most of the time, these examples are kind of broken into two parts, where given some information, they want you to solve for your constant first and then use that to help you finish up the second half of the problem. So for example, it says if y varies directly as x and y is 6 when x is 11, find y when x equals 3. So what I would suggest that you guys do is kind of think of this as two different parts of a problem. You have y is 6 when x is 11, so we're going to use that to help us find our constant. Then we're going to write a new equation to finish up for the second half of the problem, which is to find y when x equals 3. So to get started, I would begin by using this form y equals kx, and use the first part that I highlighted here in yellow to help you solve for your constant. So y is 6, x is 11, so I'm going to put 6 in for y. I'm going to leave k as k because I'm trying to solve for that right now, and I'm going to put 11 in for x. So now you have to think about how are you going to solve for your k. Well, I would divide both sides by 11 to get rid of it over here. And I'm going to have a fraction for my k, which is okay. So that's going to be 6 over 11. And I would leave it as a fraction. I wouldn't mess with changing that to a decimal. So now what you can actually do is rewrite this equation using that k that you found. So instead of saying y equals kx, we can say y equals 6 over 11x. Now we're going to move on to the second half of the problem that I highlighted in blue. They want us to find the value of y when x is equal to 3. So using this equation here, I'm going to plug in 3 for y. So I'm going to take that 6 over 11 times 3, and that's going to be 18 over 11. And again, I would just leave that as a fraction and not mess with a decimal here. So I want you guys to try to do this practice problem the same way, using that same equation. So pause the video, take a minute to try to do this problem, and then go ahead and resume watching when you're ready to see how it should have been worked out. So again, this is a direct variation. That word directly tells you that. I would break this into two parts. You've got y equals 5 when x equals 10. So we'll use that to help us find our constant. And then once we have our new equation, we'll go on and we'll find the value of y when x equals 2. So starting with y equals kx, I'm going to put 5 in for y, and I'm going to take k times 10 for my x. So I would have divided both sides by 10, which 5 over 10 can't divide nicely, but it can reduce at least. You can take a 5 out of both and get a half for your k value. So your new equation would say y equals 1/2 x. And for this second half of the problem, you were plugging in a 2 for the x, so it's 1/2 times 2. And so you get y equals 1. So that's our direct variation. Now let's talk about an indirect variation. So the indirect variation is the opposite of a direct, where when in the direct variation, your x and your y acted the same. So when one went up, the other one went up. An inverse or an indirect variation is with if one of them is getting bigger, so like let's say x is increasing, y is actually going to be decreasing. So they're going to have opposite behavior here. The equation that we use for this one is taking that form from direct variation where it was y equals kx, and we're rewriting it for our y. So we start with something like x times y equals your constant k, but more commonly you're going to see things written like this. Y equals that constant divided by x. And like I had mentioned at the start of this section, that this is going to show us kind of what our graph looks like. So we're going to start to see the graphs of a hyperbola, which is the technical name of a graph when you're having a rational expression. So when you have a fraction involved and you're trying to graph that, the inverse functions are going to look a little bit different than like a normal linear function would, and that it's not going to be a straight line anymore. I want to show you an example here of how you use the inverse variation and then show you what the graph would look like so that we can practice this. So they're going to use that word inversely in your problems to tell you that you're doing an indirect variation instead. Again, you can split this into two parts. So y equals 1 when x equals 2. That's kind of the first piece that you're going to use to help you find your constant. And then you can go on and find y when x equals 5. So you can really use either equation up here, the y equals k over x, or if you're better at doing this one, especially when you're trying to find your constant at first, maybe use that x times y equals k. So for example, if y is 1 and x is 2, and I'm using this equation here to help me find my constant, I would put a 2 in for y, a 1 in for, 2 in for x, a 1 in for y, and set that equal to k, so k would be 2. So there's your constant. So then to write your equation, we'd have x times y equals 2 now instead of k. And it wants us to find y when x equals 5. So we'd have 5y equals 2, and then we would divide by 5. And so we would get y equals 2/5. So that's solving those same types of problems that we saw on the previous page. It's just using a different formula now because we're talking about an inverse function. And so now what I want to do is take a look at this y equals 2 over 5, or since 2 is our constant, we can write a general equation as y equals 2 over x. And I could use this then to help me find any values, x or y's, to help us figure out what's going to go onto our graph. And so this is going to kind of introduce you guys to what a hyperbola looks like. So when I see a graph like this, 2 over x, if I were to look at some points, so you can see how down here I have this xy chart. 0, they have written undefined. That's because if you put a 0 in for x here, and you try to take 2 divided by 0, you're not going to be able to do that. We can't divide by 0. It's actually mathematically impossible for that to happen. So you'll never be able to divide by 0, which is why they write undefined here. And what that really means is that when we look at these graphs, think back like when we talked about those exponential graphs and how the graph was like either going up or going down, but it was like always approaching the x-axis and it never actually crossed. You're going to see that happening with these hyperbolas, and that they're going to be approaching a certain part of the graph, but they're never actually going to be able to cross it because we have like these limits or these asymptotes on our graph. So they're going to be kind of like boundary points. You can see though like what happens if I put in a -2, a -1, a -0.5. Same with the +0.5, 1, and 2. You'll notice that like your numbers here are the same. They just have opposite signs. So let's take a look at the graph. So your hyperbolas have what we call branches, and there's going to be 2 of them. So starting with the top 3 points, -2 is at -1, -1 is at -2, -0.5 is at -4. So this branch is going to be kind of in quadrant 3 here, and it's going to have that curved shape to it still, similar to like what our exponential growth and decay functions had. Now if I graph the positive side of things, it's going to look very similar here, but we're going to be up here in quadrant 1. So it's going to look like this. So as we get further into this chapter and into this section, we're going to start to explore a lot more with these types of graphs so that you can understand where you find those boundary points at, those asymptotes I was talking about. But this is just going to kind of give you a really brief introduction to how these types of graphs look like. So let's take a look at this first practice problem together here, and then you'll be able to try the next one on your own. So we're going to start again. It says that we have y varies inversely, and it says that y is 5 when x is 10, and we want to find the value of y when x is equal to 2. So we're going to start with that equation xy equals k, and I'm going to put in 5 and 10 for x and y. So my k is going to be 50 here. So then to use that, we can say xy equals 50 instead. And they want us to find y when x is 2, so I have 2y equals 50. So I would divide by 2, so y is 25. Okay, now because I found k right here to be 50, I can write that equation like this. Y equals 50 over x, if I'm talking about the actual equation for my hyperbola. So what I'm going to do here is create another xy table based off of these points. Now again, you can always put 0 in the middle and just kind of know that you're not going to actually be able to evaluate at that point, because it's always going to be undefined when you're trying to divide by 0 here. And you can use some of the same points that I used on that previous problem, so like -2, -1, -0.5, +0.5, +1, +2. And plug those in here. So you do 50 divided by -2, which would be -25. 50 divided by -1 would be -50. And then we get -100. And on the other side here we get 100, 50, 25. Now because these points are so big, you're probably going to want to change the scale on your graph a little bit, because you're not going to be able to fit 100 on a normal graph. You would need a lot of room for that. So what I'm going to do is have my graph go by tens. So for my first side, I'm going to go -2. So I'll just have to kind of, I'm going to leave my x axis the same. I'm just going to change my y axis to be going by tens. So I'm going to go over 2 and then down 10, 25. -1, 10, 20, 30, 40, 50. And again, I don't really have space to even do 10 on mine here, but I can at least sketch in what I think this graph is going to look like. And then we're going to do the same thing on the other side. So I'm going to do 1, 10, 20, 30, 40, 50, 2, 10, 20, 5, and draw that in. So again, it has the same shape that the last one did, and it's got those boundary points, where they're trying to approach like the x and the y axis there. We just had to change our scale for that one because our numbers were so big. So I'm going to give you guys this next one to try on your own. Solve the problem that they're asking for, write your inverse variation equation, and then go ahead and graph it. And then go ahead and keep watching to see what it should have looked like when you were done with it. So again, I start with that xy equals k. And the first part of the problem, I'm going to put in a 1 for y and a 4 for x. So my k equals 4. So then to write my new equation, it would say xy equals 4. And they want me to find y when x is 2. So 2y equals 4. So y is equal to 2, because you would divide by 2 on both sides. Using this right here, we can write our inverse equation to be y equals 4 over x. Then we can create our xy chart. I'm going to put 0 in the middle, and negative 2 down to that negative 1/2, positive 1/2 to positive 2. When you did this, you should have gotten negative 2, negative 4, negative 8. Can't define anything here at 0, 8, 4, and 2. And then for your graph, again, I don't have space to do the negative 1/2 and half at 8 on mine, so I'm just going to do those first 2 points and sketch in my graph. So that's what that should look like. The last thing I want to talk through with you guys is if instead of talking about a graph, they give you a table of values, you can figure out whether they're showing you an inverse or a direct variation. So this first example, we've got x's and y's provided for us. You can see that's happening in all of these tables here. The first thing that I would look at is look and see what your numbers are doing. So for my x's, it's going 3 to 5 to 15 to 17. All those are going up. And for my y's, it's going 85 to 51, 17, 15. All of those are going down. So they're behaving differently. This is probably going to lead me to think that this is an inverse variation because they have opposite behavior. One is going up, one is going down. So I'm going to say that it's an inverse function. Now they want me to figure out what my constant would be and then what my equation would look like. So in order for you to find your constant, remember on an inverse variation, we were taking x times y to get our k. So they're saying 3 times the 85, 5 times the 51, and if we kept doing this and did 15 times 17, 17 times 15, we're going to get that 255 that they have up there. So 255 is going to be your constant. So to write your equation for an inverse, it's the y equals k over x. So you would put 255 over x. And those would be what they're looking for. So take a minute and do these 2 practice problems and see if you can decide, are they an inverse or a direct variation? And then try to find your constant so that you can then write your equation for it. For the middle one here, my x's are increasing, and so are my y's. This leads me to believe this is probably going to be a direct variation because they're doing the same thing. They're both increasing. So remember, for a direct variation, it's y equals kx. So in order to solve for your k, you're going to want to take your y values and divide by your x's. So you're going to take in here 8 divided by the 0.2, 20 divided by the 0.5, and so on to find your inverse variation. So this is going to give you your constant, and these all come out to be 40. So that's your k. So down here we could say k equals 40. And so to write our direct variation, it's y equals kx, which would be y equals 40x. For the last one, if you look at your x, those are going up, your y's are going down. This makes me think this is going to be an inverse function, just like the first one was. So to find your constant, you're going to want to multiply your numbers across here. So you get your constant to be 8. So we would write y equals 8 over x.